Welcome to the Explainer. Look, if you're a data scientist, an ML engineer, or an AI researcher in healthcare, you already know the golden rule. Your model is only as good as the data you feed it. Today, we're going to radically optimize how you train your next Alzheimer's detection model. We're cutting through the noise, dropping the academic fluff, and getting straight to the data structures you actually need. So let's jump right in. Okay, let's just hit the hard truth right out of the gate. If you're building a pure EEG deep learning model and your absolute first instinct is to pull the ADNI dataset, you gotta stop right now. It's a massive trap. Relying on ADNI for pure electroencephalogram research is honestly one of the most common pitfalls I see researchers make, and it's literally bottlenecking your model's accuracy. Don't get me wrong, ADNI is the undisputed king of imaging. I mean, its fMRI and PET scan data, totally unmatched. But for ML engineers looking for clean, native, high-frequency EEG data, it's a dead end, guys. EEG just isn't ADNI's primary modality. When you're building advanced neural networks or functional connectivity models, you really don't want bolted-on secondary data. You need specialized, native EEG datasets built specifically for high-resolution temporal tasks. So to fix this, here is your map to the open-source gold mines. We're going to cover the core workhorse, the missing half, the multimodal giant, the specialist, and wrap up with a cheat sheet for choosing your exact dataset. Starting off with Section 1, the core workhorse, dataset DS004504. Released back in 2023, think of this as your reliable veteran. If you're spinning up a new resting state EEG task today, this is your gold standard starting point. Just look at this demographic breakdown. 88 total subjects, perfectly balanced between men and women. But check out the classes. We've got 36 Alzheimer's patients, 29 healthy controls, and crucially, 23 patients with frontotemporal dementia, or FTD. For AI classifiers, having that FTD group in there is an absolute game changer. It forces your model to actually learn the specific neural signatures of Alzheimer's, rather than just lazily memorizing a simple sick versus healthy binary. And let's fire off the hard specs, because this is where you're really going to appreciate this data. We're looking at a 500 Hz sampling rate across 19 channels with a really solid 12 to 14 minutes of recording per subject. It's a resting state, eyes closed setup. But the absolute best part? It comes packaged in native BIDS format. That means raw data and clinical info right out of the box. You can literally pull it straight into your Python pipelines like M&E Python or PyTorch with almost zero data wrangling friction. Moving to Section 2, the missing half. This is dataset DS006036, dropping in 2025. I call this the missing half because it is the literal complement to our previous workhorse. It features the exact same 88 subjects, matching the 500 Hz rate, the 19 channels, and the BIDS formatting. But here's the twist. The conditions are completely changed. Instead of resting state, this dataset captures the patients with their eyes open, and it introduces photic stimulation, flashing lights used to trigger neural responses. If you're doing contrastive learning or need dynamic state variations from the exact same brains, pairing these two datasets gives you a massively robust training foundation. Now here's where we pivot a bit. I know some of you are probably thinking, okay, I love the clean EEG, but my architecture is multimodal. I kind of want that massive ADNI-like variety, but I absolutely refuse to compromise on EEG quality. Well, I've got exactly what you need. Welcome to Section 3, the multimodal giant, PEARL-Neuro Dataset DS004796. This is a serious heavy-hitting dataset. Now, a quick distinction. While the first two focus on diagnosed patients, PEARL-Neuro actually focuses on healthy individuals who are at risk of Alzheimer's. And the very first thing that jumps out is this number right here, 1,000. That's a 1,000 Hz sampling rate. For feature extraction, that's an absolute goldmine. Capturing ultrafine neural oscillations at that speed allows your deep learning models to catch subtle microstates in the brain that a 500 Hz rate will just completely smooth right over. And the depth of this dataset is honestly wild. We've got 79 subjects tracked across 235 distinct recording sessions. And it's not just the 1,000 Hz speed, it's the density. We're talking massive 127-channel EEG arrays. Plus, true to its multimodal nature, for a subset of participants, it includes fMRI scans, genetic info, cognitive testing, lifestyle data, you name it. If you're designing advanced multi-branch neural network architectures that fuse high-density temporal data with spatial and genetic inputs, PEARL-Neuro is basically your new playground. All right, Section 4, the specialist, the TMS-EEG Dataset. So this dataset steps completely away from standard resting states and moves into highly controlled stimulus response analysis. How does it work? Well, first, researchers apply transcranial magnetic stimulation, or TMS, directly to the subject's brain. Think of it like a targeted magnetic pulse. Then, they immediately record the brain's direct electrical reaction using high-density EEG. You aren't just observing a quiet brain, you are actively pinging the network and measuring the echo. For AI models focused on functional connectivity, this cause and effect data is incredibly potent. Now, because of the complex physical procedure required to actually gather this data, the subject pool is a bit smaller, but it is impeccably balanced. Exactly 17 Alzheimer's patients and 17 healthy controls for 34 subjects total. For ML engineers, having a perfectly balanced dataset like this is just ideal for those highly controlled, binary classification tasks where you really want to minimize class imbalance biases. And finally, Section 5, choosing your dataset. Let's look at the ML cheat sheet. We've covered a ton of ground, so let's set up a quick decision-making framework for your next project. Looking at this matrix, if you're building a foundational model and just need a large, clean, balanced cohort, grab DS004504 and its active state sister, DS006036. If your hardware can handle massive dimensionality and you're predicting for at-risk populations, step right up to PEARL-Neuro with its 127 channels and 1000 Hz resolution. And lastly, if you're analyzing direct network perturbation, the TMS-EEG dataset gives you that highly specialized cause and effect data. So here is the big takeaway, guys. It is time to stop wrestling with generic datasets that just weren't built for your specific needs. The majority of new cutting-edge papers in Alzheimer's EEG detection and graph analysis, they are leaning entirely on these specific open-source goldmines. Because they use the BIDS format, you can pull them directly via Python today. Skip the data cleaning nightmare entirely and jump straight into training. The links to the metadata and APIs for all of these datasets are out there waiting for you. You've got the tools, you've got the Python libraries, and now you have the ultimate map to the highest quality data available. So I'll leave you with this. Which of these datasets is going to power your next deep learning breakthrough?